One possible derivative of our reconstruction could be a 3D model prepared for the use in augmented reality, AR. This technology differs from virtual reality, VR, which completely immerses users in virtually rendered environment. AR overlays digital information such as 3D models, images, and metadata onto the real world through devices like smartphones or tablets. It can serve as a powerful tool to visualize historical structures that no longer exist. This technology combines real-world sensory input with computer-generated real-time content using simultaneous localization and mapping, SLAM. This process involves the three main steps. First, the AR device senses the environment with camera or GPS to track the position and orientation of the user and their device. Next, the system analyzes the sensor data and identifies objects or features in the environment for display. It uses image processing and recognition algorithms to identify and track these objects in real time. Finally, computer-generated content is rendered and displayed on top of real-world environment. This step ensures that virtual objects appear in the correct perspective and position relative to user's viewpoint. The most popular and widely used solutions for augmented reality development include ARKit, developed by Apple for iOS, ARCore, developed by Google for Android, and finally, accessible for free game development engines Unity and Unreal Engine. There are various types of AR, each distinguished by its specific features and applications. Marker-based AR relies on physical markers, such as QR codes, to trigger digital content display when viewed through an AR device. Markerless AR, or location-based AR, utilizes GPS, digital compasses, and accelerometers to provide the data and augment the environment based on the user's location. Projection-based AR involves projecting artificial light onto physical surfaces and detecting human interaction with it. Superimposition-based AR offers the perception of the environment by replacing or overlaying the original view with augmented content, either fully or partially. Each type of AR offers unique ways to enhance our interaction with the world around us. Although AR's potential is tremendous, there are some limitations. Displaying complex 3D scenes in real time often involves extensive data transfer. It also requires substantial bandwidth and computational power which mobile devices lack. To prepare 3D models for AR use, optimization is key to ensuring smooth performance and usability on mobile devices. It can be achieved by following several guidelines. Firstly, we need to simplify model geometry without losing visual fidelity. For instance, a chair model with an initial vertex count of 6,500 can be optimized to 500 vertices while maintaining its recognizable form. Models should be also divided into smaller parts to prevent device overload. Limiting models to 65,000 vertices per segment is advisable to ensure compatibility with existing hardware. The standard is also to use squared textures with dimensions that are powers of 2, such as 1024 by 1024 pixels. What is more, we should make sure to use one measurement system like meters or centimeters to avoid discrepancies and place the pivot at the center of the object to allow accurate rotation and movement of the model. The mesh of the model should be triangulated, while quads or parametric surfaces can be problematic. During exporting, we need to include normals and texture coordinates to ensure accurate rendering. When it comes to file format, it is recommended to use OBJ due to its efficiency, well-established standard, and wide support. Formats like FBX and Collada are commonly used but tend to be bulky. Advanced techniques can further enhance model efficiency. Applying textures and lighting significantly improves visual quality while reducing computational load. Baking light and texture details onto simpler geometry can create visually detailed models without excessive vertex counts, resulting in better overall performance and user experience.